Welcome to the CWI Deep Dive Podcast series. This is one episode in a series of 11, each covering a chapter of Welding Inspection Technology. These podcasts are designed for inspectors preparing to take the American Welding Society Certified Welding Inspector exam. They are not meant to replace enrolling in a Certified Welding Inspector preparation course or dedicated self-study, but to complement them. Along with our CWI Test Prep app, available on the Apple App Store, these podcasts will help strengthen your preparation. You can continue learning at work, during your commute, or wherever you find time. Today's episode is brought to you by AMS Level 3, providing consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. Learn more at the link in the video description. And just a quick note before we jump in. This podcast is an independent educational discussion based on concepts from the American Welding Society's Welding Inspection Technology book. We are not affiliated with the American Welding Society, and this podcast is not a replacement for purchasing or studying the original text. Our goal is to provide commentary, explanations, and reinforcement to help inspectors prepare for the Certified Welding Inspector exam. Okay, so if you're getting ready for that AWS CWI exam, you already know saying, the welds look okay? Well, that doesn't cut it. Welding inspection is really built on documentation, governance. You need that paper trail, the legal authority, and solid proof of qualification. So welcome to the Deep Dive, our mission today, to really get into Chapter 6, Documents Governing Welding Inspection and Qualification. Think of this as your shortcut to understanding all that essential paperwork, from codes to qualifications that lets you verify quality way before, during, and even after the arc strikes.
Just a quick interruption to introduce a resource to help you take your training further. The AMS Level 3 CWI Part A Test Prep app is now available on the Apple App Store. Designed for welders and inspectors preparing for the Certified Welding Inspector exam, it offers two modes. Study mode gives instant feedback with detailed explanations, and test mode simulates real exam questions with topic-based results to track your progress. All questions align with the AWS Welding Inspection Technology reference, ensuring accuracy and relevance. Download the CWI Part A Test Prep app today on the Apple App Store and take your study time to the next level.
Absolutely. And, before any fabrication even kicks off, the inspector really needs to put on their, let's say, their contract lawyer hat. Your first big job is that pre-job review. You need to dig into the drawings, the codes, the standards, and any project specifications.
Okay, let's unpack that review a bit. What are the really critical pieces of info you're trying to pull out there?
Well, it's pretty much everything that governs the job. You need to understand the geometry, obviously, the base metals, the filler metals, what welding processes are allowed or required, the NDT specs, and crucially, the acceptance and rejection criteria. What makes a weld good or bad according to this job? But it's more than just, making a list. You're figuring out the whole workflow, the rhythm of the job, as you said.
And a key part of that rhythm involves something you really have control over as the inspector, establishing those hold points.
Exactly. Hold points are absolutely critical. They are mandatory stops in the fabrication sequence. Work literally cannot move past that specific point. Maybe it's after fit-up is complete, or perhaps before a root pass gets covered up until you, the inspector, perform your check or inspection and give that formal, usually written, approval.
Right.
And think about the impact. If a hold point gets missed, you could be forcing a company to tear apart something almost finished just to verify something that should have been checked hours or days ago. You're the quality gatekeeper there.
Makes sense. So let's start with maybe the most visual part.
Yeah.
The drawings. They give you the graphical picture, right? Locations, lengths, weld sizes, and maybe special instructions like preheat or even the camber needed for a beam.
Precisely. And you'll often see dual dimensioning on drawings, especially if it's an international project. You'll get the U.S. customary unit, say 1.50 inches, followed by the SI unit in brackets like 38.1 millimeters.
Why bother with both?
Well, it's all about preventing errors. Engineers want to make sure different teams, maybe using different systems, reading the same print, don't make conversion mistakes. It's really a layer of QA built right in.
Got it. And another detail you absolutely cannot miss on a drawing is the tolerance.
Oh, yeah?
Tolerances define that total wiggle room. the permitted variation from the exact design size. You need to spot these quickly. Like, they
Yeah.
might be shown as limits, say 1.373 to 1.377 inches.
Right.
Or maybe as the main size plus or minus something like 1.375 newly divide Boyd 002.
And watch out for those sneaky one-sided tolerances. If they only give you one value, the other side is assumed to be 0. So if you see a dimension listed as, say, ½ an inch plus 1/32, it means the minus tolerance is 0.
Yeah.
That part cannot be any smaller than ½ an inch, period.
Good tip. Also, drawing notes. You have the general notes, they apply to the whole drawing, often with that little phrase, except as noted. And then the local notes, which are specific to one area, usually pointed out with a leader line. A sharp inspector knows to look for those exceptions that might override the general rules.
That's right. Knowing where the exceptions live is key.
Okay, moving from the pictures, the drawings, to the sort of legal backbone. Codes and standards.
Yeah, and this is where the language gets really important. If AWSD 1.1 is like your go-to guide for structural steel, then ASME is the massive encyclopedia for anything holding pressure. Codes are essentially the law for that specific contract. Once a code is invoked in the job specs, it's enforceable, it's mandatory. That's where you see the critical word shall.
Right, shall means you must do it. And the AWS D1.X series is huge for structural work. D1.1 for steel, D1.5 for bridges, and so on. But if you're inspecting pressure parts like pipes or vessels, you're living in ASME land. Codes like B31.1 or B31.3 for piping.
Exactly. And within the big ASME boiler and pressure vessel code, all those volumes, you absolutely need to know your way around Section V, which covers NDE and, critically, Section IX. That one covers all the qualification requirements for welding, brazing, and fusing. Super important.
So how are standards different from codes then?
Well, standards are more like guidelines. They represent the industry's view of best practice. They often use softer words like should or maybe may. Think of something like ASNT's recommended practice SNTTC 1A for certifying NDT personnel. It's non-mandatory on its own.
Okay.
It only becomes mandatory, like a code requirement, if the main contract or the governing code explicitly adopts it or calls it out.
And then specifications fill in the gaps, right? They give you the really fine details.
Precisely. Specs can be industry-wide, like the AWS A5.X series that defines filler metals, or they could be totally unique in-house specifications written just for one customer's specific needs.
Okay, so we've got the design document sorted. Now let's talk about controlling the actual stuff, the metal itself. Material ID and traceability seem critical, especially for like nuclear or pressure vessel work where a mix-up could be disastrous.
Oh, absolutely catastrophic. This is where the MTR, the Material Test Report, sometimes called an MTC, Material Test Certificate, comes in. This is a notarized document straight for the material manufacturer. It lists not just the typical properties the spec requires, but the actual measured chemical and physical properties from that specific batch, that specific heat number of material.
So as the inspector, my job is to take that MTR, review it, make sure it meets the project requirements, and then physically compare it to the markings on the steel, the type, the grade, the heat number, stamped or stenciled right there.
That's the fundamental check. But,
Right.
you know, paper can get lost, markings can get smudged, mistakes happen. This is why we're seeing more and more emphasis on PMI, positive material identification.
The alloy analyzer gun.
Exactly. You're using a device, often an XRF analyzer, right there on the shop floor to confirm the alloy chemistry directly from the metal itself. You're not just relying on the paperwork. For really critical stuff, materials might get PMI'd 100% just to be absolutely certain it's the right alloy.
Okay, so we've proven the material is correct when it arrives. Now the challenge is keeping track of it right. Maintaining traceability, making sure every little piece cut from that original plate or pipe can be traced back to its MTR throughout the whole fabrication process.
Yeah.
How do shops manage that without going crazy?
It's a balancing act, definitely. You need to meet the requirements, but it has to be practical. You know, simple segregation on marked racks might work for less critical materials. Color coding is really common.
Right, paint stripes.
Yeah, but color coding has pitfalls you need to watch out for as an inspector. First, will the color actually last? Think about outdoor storage, weather exposure. And second, and this is critical, you must ensure the marking material itself isn't harmful to the base metal.
Like using high chloride markers on stainless steel.
Exactly. That's a classic mistake. High chloride contamination can lead to stress corrosion, cracking, and austenitic stainless steels down the line. Big problem. So, low chloride markers are essential there.
That's a huge point.
Wow.
What else?
Well, you see alphanumeric codes, short codes like A1, B2, just to simplify tracking instead of writing out long heat numbers everywhere, and increasingly barcodes. They're great for inventory control and making the tracking process much more automated and less prone to human error. Probably the way forward for most.
Makes sense.
But here's a vital detail, no matter what system you use. Identification markings, the heat number or trace code, must be placed on diagonally opposite corners of plates. And for pipes or bars, it needs to be on both ends.
Why is that so specific?
So that if the material gets cut in half or into smaller pieces, both resulting pieces still have the identification mark. You don't lose traceability just because you cut the material.
Ah, clever. Ensures the ID survives the fabrication process itself. We'd also like to recognize Skaggs Media LLC as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com. Okay, so we've got the material under control, we've got the governing documents lined up. Now we have to make sure the welding itself and the people doing it are also qualified and controlled. Let's shift to procedures and personnel qualification.
Right, and procedure qualification has to come first. You have to prove the recipe works before you let anyone cook with it, so to speak. The whole point of qualifying a welding procedure is simply to demonstrate that the proposed combination, the process, the base metals, the filler metals, the technique, can actually produce a sound weld. It is not about testing how good the welder is.
Not about welder skilled at this stage.
Okay.
And there are different ways to qualify your procedure.
Primarily 3 ways, yeah. For structural steel, under AWSD 1.1, you have the unique system of pre-qualified procedures. This means certain common combinations using processes like SMAW, SAW, FCAW, or GMAW, but not short-circuit GMAW with specific materials and joint designs don't actually require any testing, provided you follow all the rules laid out in the code.
Saves a lot of time and money if you can use one of those.
Definitely. But for many other codes, like ASME, or if you fall outside the pre-qualified limits in D1.1, you need to do actual testing. This involves welding a test coupon, cutting specimens from it, and doing destructive tests, usually tensile tests to check strength, and bend tests to check ductility. Sometimes also things like nick break or fillet weld break tests. Remember that pronunciation? Fillet.
Fillet break test, got it. And the third way?
The third approach is using a mock-up. This is usually reserved for really complex joints, maybe with very high restraint, or where access is going to be extremely limited in actual production. The mock-up tries to simulate those challenging conditions.
Okay, let's clarify the paperwork trail here because it gets confusing.
Yeah.
You have the PQR and the WPS.
Right. Think of it like this. The PQR, the procedure qualification record, is like the lab report. It documents the actual variables and conditions that were used when welding that specific test coupon. It's the raw data, the proof.
Okay, the record of the test.
Exactly. Then, based on that successful PQR, you write the WPS, the welding procedure specification. This is the actual set of instructions, the recipe for production welding. The WPS doesn't list the exact values from the test. Instead, it lists the range of variables you are qualified to use in production based on the code rules. These are the essential variables.
Essential variables.
Oh,
Those
God.
are the critical things that if you change them too much, you have to requalify the procedure, right?
Yeah.
Like changing the welding process or maybe the base metal thickness group or adding preheat.
Precisely. Changing an essential variable beyond the limits allowed by the client invalidates the WPS, and you need a new or revised one, possibly supported by a new PQR.
Okay, so procedure is qualified, WPS is written, now we worry about the welder skill.
Now we focus on the welder. This is welder qualification, and the documentation is the WQTR, the Welder Qualification Test Record. This test is purely about determining if the individual welder has the necessary skill to deposit sound weld metal using a specific WPS.
And the essential variables for welder qualification are different then, because it's about their physical ability.
Exactly. Welder essential variables focus on things that directly impact the welder's manipulation and control. Things like the welding position, flat, horizontal, vertical overhead, the joint type, groove or fillet, the thickness of the material they weld on the test, the direction of welding for vertical position, uphill versus downhill, whether backing was used or not. It's all about what challenges their physical skill.
And thickness qualifies is a big one on the CWI exam, I hear.
Sure.
Can you break that down, like the 38-inch versus 1-inch plate test in D1.1?
Sure. It's a common point of confusion. Under AWSD 1.1, for example, if a welder successfully passes a groove weld test on a 38-inch thick plate, they get what's called limited thickness qualification. Typically, this qualifies them to weld production material from 18-inch up to twice the test thickness, so 34-inch in this case.
Okay, limited range.
But if they successfully weld a 1-inch thick plate for their test, they generally gain unlimited thickness qualification. That means they're qualified to weld material 18-inch thick and greater, so that one test covers a much broader range.
So testing on thicker material gives you more bang for your buck qualification-wise.
In terms of thickness range, yes. And if you really want the broadest qualification possible from a single test, you aim for the 6GR position test.
The pipe fixed at a 45-degree angle. What's a restriction ring all about in the 6GR test? Is that just to make it extra difficult?
It's not just difficulty for difficulty's sake. That restriction ring, usually placed about an inch away from the weld joint, simulates the physical obstructions you encounter when welding complex structural connections in the field, specifically things like T, K, and Y connections on pipe or tubular structures. Access is often really tight.
Okay, so it mimics real-world challenges.
Exactly. By passing that 6GR test, welding around the fixed pipe at 25 degrees with that ring-limiting access, the welder proves they can handle the most challenging positions and access limitations. Passing 6GR typically qualifies the welder for all positions on both plate and pipe, including those tricky T, K, and Y joints. It's often considered the pinnacle test.
Wow, okay, that's a really valuable qualification to have. What about electrode groupings, like F numbers for SMAW?
Yeah, the F number system group that's MAW electrodes based on their usability characteristics, essentially how difficult they are to handle. F1 electrodes are generally the easiest. F4 electrodes, like low hydrogen electrodes, are considered the most difficult. The general rule is if you qualify using an electrode from a higher F number group, say F4, you are automatically qualified to use electrodes from all the lower F number groups, F3, F2, F1 as well. It streamlines things so a welder doesn't need a separate test for every single electrode type.
Saves time and paperwork again.
Yeah.
So just to be crystal clear on terms, qualification is the demonstrated skill proven by the test.
Right.
And certification is just the piece of paper, the WQTR, that documents that qualification.
You got it. Certification is the documentation. Qualification is the actual ability. And it's important to remember that qualification isn't necessarily permanent. While it typically stays valid as long as the welder keeps using that process successfully, if you, as the inspector, observe poor workmanship or have reason to question their ability, you absolutely have the grounds to require requalification testing.
Right, performance on the job matters. Okay, so let's try to pull this all together for you listening. This deep dive shows that welding inspection isn't just about looking at finished welds with a flashlight. It's really about mastering these 4 core document types: the drawings, codes, standards, and specifications, and then understanding how material control and the whole qualification testing framework for both procedures and people create the system that lets you enforce quality, starting way before any welding actually happens.
Absolutely. And maybe here's a final thought for you to chew on as you prepare. Remember that qualification tests, both for procedures and welders, are often done under pretty ideal conditions. Clean environment, perfect fit up, good access, much nicer than the shop floor sometimes. The real mark of an excellent CWI isn't just knowing the rules on paper. It's using that knowledge of qualified ranges, essential variables, and potential difficulties to spot inconsistencies out on the floor, maybe poor fit up, or access issues that weren't simulated in the test before they lead to bad welds. Applying that knowledge practically, predictively, that's what truly separates a good inspector from a great one.
Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training, and mentorship, or compliance solutions like NADCAP and Federal Aviation Administration readiness. To learn more, visit amsl3.com, and don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support: NDT Level 1, $1 per month; NDT Level 2, $2 per month; and NDT Level 3, $3 per month. Or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.